yeah, my name is Christoher Chedeau, and oops. I've done a lot of things that are related to React, like as she mentioned, but this time we're going to do something like talk about something very different, which is about video editing in the browser. So during the pandemic, I spent a lot of time editing videos, and at some point I did enough that I was thinking maybe I should become a YouTuber, like full-time, quit my job. Now, if you look at the number of views, I should probably stay at Facebook for a little while. So what does video editing mean? So in practice, I bought a $20 green screen that I put in my mirror, and I started using Final Cut Pro. And so one of the things I felt like was like basically back 20 years in the past. And for example, like right now with Zoom, you're expected to be able to remove the background automatically. But here I had to find like the green color and the ranges of color, and like there was a shadow, and it didn't really like disappear, so it was pretty manual. And same like when I'm talking right now, we have this amazing speech to text, and I didn't have this. In Final Cut Pro, you have like the sound waves, and it's like not very useful. So I'm a front-end engineer. I was like, okay, I'm going to spend some time implementing this in the browser. And one thing that's happened in the browser ecosystem is I felt like we had all of the tools to do it. So for example, with web codecs, we are able to do encoding and decoding in the browser. Now with TensorFlow.js, we're able to remove the background. With Whisper, you're able to get the text and get the speech and put it into text. So I felt like, okay, I'm going to do it. It's going to be easy. Now, spoiler alert, it was not. And usually when I go into those projects, there are some like things that I think are true that I'm going into the project with. And in this case, like there were 3 things that I thought were true that weren't. So the first one is that time only travels forward, which seems logical, but wasn't true. The second is, if you decode 1 frame, you're given 1 frame back. Again, this was not true. And the last one is, WASM is faster than pure JavaScript for video decoding. And so those are 3 things that were like, oh, this is obvious, but it wasn't. And so today we're going to go through the tale of like everything I discovered during this journey and see why they weren't. So let's think about what is the problem, like the project I wanted to go about. So imagine you have like a super video about RemixConf, and it starts with like the logo sideways, and like it starts like going in the full screen, and like I'm not a good designer, so like this is the best I could do. And we want to like start modifying it, manipulating in JavaScript. So this is the API I expected for us to like have. So it was like a load video function that takes a file path and gives me an array of images. Then I would modify the array, I would run TensorFlow, I would do a bunch of things like crop, like move things around, and then I would have a function save video, take a file path, and a list of images. So, okay, it seems like a pretty like simple enough API, but why doesn't it work? So for this, we have to go a bit into like how is an image actually encoded like in binary, like how is it represented in the device. So let's look at the image. So in order to know how many pixels you need for the image, you use like the width multiplied by the height, and you get around like 1.3 megabytes. Then each pixel is commonly represented at 3 components, red, green, and blue. And so you multiply by 3, you're already at 4 megabytes. And this is just for 1 image. Now we all know that like an animation that runs at 60 FPS. So for 1 second of video, if you encode it like this, it would take like 200 megabytes for 1 second. My talk right now is 20 minutes. So I can let you imagine like how big that would be. So the API that we were thinking about to load the video and get the array of all of the images like would run out of memory even for like super tiny videos. So we are there, like, what can we do about it? So the obvious solution is to get a shrinking machine, obviously. Now, what does it mean like for software engineers? So in practice, we're going to use techniques called image compression to be able to like shrink the image. So the part of this talk is going to be a bit technical and like math heavy and everything, but the thing I want you to get out of it is like what are the concepts, the high level concepts, and less about like the specific details. And the reason for this is the concept that we're going to talk through are going to have a major impact on the API that we actually have to play with. And they are needed to like actually use this API. So let's go. How do you compress an image? So this is like a small part of the remix image. And as you can see, there's like basically only two colors in this case. There's like red pixels and black pixels. So the idea for this is, well, I'm going to start encoding one pixel, one pixel, but you can see like there's like 5 or 7 pixels in a row that are like very similar. And so instead of encoding dark, 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 like 5 times, I could just like have one byte that says like how many of the pixel I want, and then the pixel. So this is able to like start compressing. So this technique is called run length encoding, RLE. And so this is very useful for this kind of images. But as you can, like I probably expect, like if I take a picture of like all of you right now, like you're never going to get like 5 dark pixels in a row. Like it's going to be like a gradient and everything. So this technique alone is not going to cut it, but it's part of a pipeline. It's part of like we are going to see 2 other techniques that can be combined together in order to improve the image compression. So this was the first one. The second one, you need some imagination. So instead of looking at the image as a series of pixels, we're going to think of the image as a continuous function. The same one you've heard in high school and in college in math courses. It's actually useful in practice. And this is basically like a continuous function. And one of the theorems that exists is that you can decompose any arbitrary continuous function into a sum of sinusoidal function. So this is called the Fourier transform. And so you're like an infinite sum of the sinusoidal function. And the idea for this is, as you can see in the illustration, the first few sinusoids are like really big, and they basically capture the information, like the most salient information in the image. Now, if you want to actually encode all of this, each of the sinusoids actually takes the same number of bytes to encode. And so the idea behind this optimization is that you're only going to encode like the first few ones that represent most saliently the image, and the rest you're not going to encode. And so this way you're able to destruct, like remove some information that is less visible and less useful for the image, and therefore you're able to compress the image. So this is the second technique. The last technique, we're going to think of the image again in a different way. Now, instead of thinking as a series of pixels or a continuous function, we're going to start thinking about it as a series of zeros and ones, like bits. So I know as front-end engineer, like we rarely have to think about it, but in practice, if you dig deep down, like this is how everything is encoded. And so now that we have this, one of the things we can start looking at is how many of each patterns are there. And so in this case, the pattern 0101 is present 15 times. The pattern 110 is present 7 times. And then there are some patterns, for example, like 101, that's only present 1 time. So now that you have this, the idea is to do a remapping of the common patterns into like fewer bits and the other pattern into like more bits. So in this case, what we can do is to remap the pattern 0101 into like a single bit. So if you see 0 anywhere in the stream, we're going to replace it by 0101. And then the pattern 110 in 2 bits, 10. And then we're going to keep going. And at some point, the first few ones we're going to give like smaller number of bits, but we cannot have only smaller number of bits, so the last ones are going to be larger. But because they only appear so few times, in practice, it's going to compress. And so one of the last things we need to think about is we also need to ship the compression table, and hopefully, if the data is compressible, if you add the compressed data plus the decompression table, you're going to get a smaller image. So now that we've seen those three techniques and you can combine them together, what is the impact on our image size? And so in practice, this is like very rough order of magnitude, but we can divide by 10 the size of the image. And so instead of having one image like weight 4 megabytes, now it's 400K. So it's much better. And the name of the compression algorithm are JPEG, WebP, PNG, just for your culture. So now it's still a bit too much. Like 23 megabytes per second is much better than 200, but it's still a lot. And so this is where the people working on like image compression and video compression like, well, like, okay, they have more ideas. They have like ways to get better. And so in this case, the fundamental thinking around this is instead of thinking of the image as like one image and one image and one image and one image, what we can do is to think of the video as like sequences of image, and all of the images that are neighbors tend to be very, very similar. So in this example, we do a transition, but all of the frames like subtly change. And so this is where like the next idea around like video compression comes in, is instead of compressing only single image, we're going to start thinking of doing a delta of the image. So in this case, the two images, only 3 pixels are basically changing. And so we're going to start encoding only what changed between the two images. Now, we can even do better. What we can do is to start predicting what the next image is going to be. So in many cases, the transition are like animation that like goes somewhere. So in this case, sorry. In this case, the remix is slowly translating. And so the video encoder can start predicting what the next frame is going to be based on the previous ones. And then we can do a delta of the difference. And so the name of this step is like a codec. And so the major codecs are H.264 and AVC. And so in this case, the two are exactly the same thing. This is like I'm sorry. This is like JavaScript and ECMAScript. There's some trademarks and everything involved, but they are the exact same spec. And then there's AV1 and VP8, VP9. So what does it mean? Like this is nice, and I think you can follow like how this works. So how does it work for like our API? So now, the interesting thing about this is there's now 2 types of frames. There's full frames. So for example, like the first one. So the first one, where you need to like use JPEG or something to decode it, but it works in isolation. And then the second one is like the prediction plus the delta. And so now in order to decode the frame number 2, you need to have decoded frame number 1 and have the information of number 2. And same, like there's a chain. Well, like now if you want, if you want to encode frame number 1, you need to have decoded in order like 1, 2, 3, 4, 5, 6, 7, and 8. So this is like going to have some impact on the API. But the people working on video compression were not done yet. They were like, okay, this is nice and fancy to do it like in this order, but we could also set that the frame number 9 is a full frame and do it backwards. And then start like doing the whole prediction backwards. And then you can start doing it forward, doing it backward, and see which one has the smallest file size. And so this is where the notion of B frames comes in. So in this case, the frame number 5 is bidirectional. So in order to decode it, you need to have decoded frame number 4 and frame number 6. And so, sorry about this. In order to 6, you need 7 and 8 and 9. And so now this is where it gets interesting for the API, is now what you need to do is to be able to send the things to the decoder in the right order. So if you want to decode in the order it's going to be displayed, like 1, 2, 3, 4, 5, 6, 7, and 8, and 9, you need to actually send to the decoder 1, 2, 3, 4, and then 9, 8, 7, 6, and 5. And so there's 2 notions of time that are happening. There's the there's a presentation time, which is the one you expect, and then there's the encoding time. And so you need to understand like those two concepts in order to use the API. So now let's look at, and so this is our first like myth that got busted. Like time doesn't only travel forward when you're thinking about video encoding. So now let's actually look at some code. So now the video is there still some kind of a load video API that takes a file path. And now there's a new concept that you need to understand is a decoder. And so this is what is called a web codec, the API in the browser. And that is a new video decoder. And there's a bunch of options. And like in one of those options, there's a callback on decoded frame. And so now what you want to do is to send it frames to decode. And so the load video is going to give you some kind of magical API to give you like frame number 1. And then at some point in the future, the callback is going to be called for you. And then you're going to do it. And this looks like code you've seen like many times. You're giving the frame 2 is going to give you the frame 2, etc. But at some point, you're now going to start giving those frames in a different order. So you're going to give frame number 9, frame number 8, frame number 7, frame number 6, and it's never going to call your callback because it doesn't have enough information to actually give you the thing in the presentation time. But at some point, you're going to give frame number 5, and now it's going to give you call your callback, everything in order. And so this is where our second myth got busted. Decoding 1 frame gives you 1 frame back. And now if you think about it, like I've programmed for like 20 years, and I've never seen any API that doesn't predictively give you like a response or not. And in this case, you can give it 5 things, it gives you nothing, and that's like the 6th one gives you like 6 results. And so this is like a bit mind-bending to figure out like how do you schedule all of these events where like you don't know in advance like how things are going to go. So this is like some of the API, like the web codec API, but there's still like this question of like the magical load video API. So if you were to like start thinking about like how would you represent like all of this metadata we're talking about. So we're talking about like what are the dependencies between all of the frames. We're also thinking about what are the like binary data around like the compressed images and everything. How do you present it? So in practice, I'm a front engineer, so my thinking is in JSON. So I would think of a JSON like this, JSON structure like this, where you have like some general information about the video, and then some tracks, a video track, and a bunch of frames, and then a bunch of like list of dependencies. And so this is something that is called a video container. So the art and the data structure to like store all of this metadata is a video container. And this is something you're most likely familiar with. You've seen like MP4, MOV, MKV, AVI. So all of those are video containers. Now, they were not built by front-end engineers, so they're actually all binary encoded formats. But if you actually look, this is basically a tree structure like a JSON. Now, this is this step of like reading this file and sending it to the decoder is called demuxing. It's called demuxing. And one of the challenges that you're going to face if you want to use in the browser is that the web codec, which is like doing the hard and heavy lifting of like decompressing, like prediction and everything, is part of the browser, but the demuxing is not. And the reason for this is all of those video formats, like there's so many variations that in practice, as they start working on the API, they decide to like reduce the scope. And so you need to find the right libraries in userland in order to use this. So now that we've seen like the whole pipeline of like how the API works, there's still one question that people are thinking about is like performance. What about performance? And there's actually 2 steps for the performance. So the first step around performance is like the video codec one. It's to actually do all of this compression, decompression, delta frame prediction. And so in practice, this part is so performance intensive and so critical that there's actual hardware implementation of the Hoffman encoding, of the fast Fourier transform, like of all of the steps I talked to you at the beginning in the hardware. And so like next to your CPU, next to your GPUs are dedicated chips for doing those operations. And one of the things is that's like very good about web codecs is that it lets you use those hardware accelerated components to be able to do those operations. And so now if you're thinking about WASM, so first you would have to write it in C++ running on the CPU, and even this is like an order of magnitude slower. So even if you have like C++ and everything, you still won't match the performance. And now with WASM, there's some overheads of running WASM compared to pure C++, and so you got another like slowdown. And so this is why using JavaScript to send to the browser, and that's going to send to the web codec and the hardware, is faster in JavaScript. Now, there's a second part which is around like the demuxing part. So reading this file and being able to like send to the web codec. And so for this, you may think, okay, I'm going to read this, like writing C is going to be faster. Now, one of the things is the demuxing part is actually not the most expensive part. And for this, to get an idea is the binary data that we have is tens to hundreds of kilobytes of data. But now, each line is like tens of characters for each frame of overhead. And so like parsing tens of characters is like way faster than like doing all of this processing. So this is one step. And the second one is the way WASM works is it has its own memory pool. And in order to call to it, you need to send all of this data to this memory space. It does this work, and then it's going to send it back to you. And here we're talking about like megabytes or like tens of megabytes. So you need to do this copy first and then copy back. And so in practice, do it in pure JavaScript, avoids this copy, and is faster. So this is our third myth that got debunked. WASM is actually not faster than JavaScript for video decoding. Now, I want to put a small asterisk to this. So as I mentioned, the demuxing part is not part of the browser. But like all of those codecs have been there for like decades, and and there's a lot of C++ libraries that are really, really good and battle tested around this. So we can actually use those with WASM in order to like do code reuse and use the ecosystem that already exists in order to re-implement it. And we're going to get a slow performance degradation, but in the end, it's worth it to not have all of the bugs. So now that we've seen like the three myths and everything, what about the initial like premise of my talk, which is, oh, we're going to build like a video editor with like all of the shiny AI stuff? Well, unfortunately, I wasn't able to get there because I spent all of my time trying to get like just encoding and decoding run it. Now, what this means is I actually succeeded at this. And so I have like a raw HTML5 with no dependencies, like it's 200 lines to do all of these steps that I talked to you about. And in practice, one of the great things is that it actually works. Like you can re-encode a video. And the second thing, it's really fast. So I compared it to Final Cut Pro re-encoding and to like the browser, the same performance. Like, so it's possible, and the perf is there. Now what's needed is like someone to like really make the API good. And so Dan was like doing like a talk about like a different dimension, like talking about IE6 and everything. So my challenge to every single one of you is, who's going to be the one that builds the jQuery of video editing? Because this is what we need right now. Thank you.